So we're going to jump ahead a little bit and look at solutions. Solubility is the ability of a substance to dissolve in another substance, and it is definitely affected by intermolecular forces and the structure of a particle. So we've got different parts of our solution. The solvent is the substance that's doing the dissolving. It's often water. It's often the particle that's present in a greater quantity. The solute is whatever you're trying to dissolve. It could be a solid, a liquid, a gas. Solvation is this process of dissolving in your solvent, which we're going to use water. And then eventually we form an aqueous solution, which is when something has dissolved in water. That's what aqueous means, dissolved in water. Now there's this rule of solubility. It says like dissolves like. And by that we mean polar substances only dissolve in polar solvents. A nonpolar substance would only dissolve in a nonpolar solvent. And so solubility then depends on the polarity of the substance. And so here it says polar compounds in water. Polar compounds in water. Well, let's look at a water molecule one more time. When we've been drawing its dot structure, which we're getting really good at, right? Here's the dot structure of a water molecule. And I've got my hydrogen 1, my hydrogen 2. It's a bent structure. It's a polar molecule. The oxygen has a high electronegativity. So the electrons are pulled up toward the oxygen, making the oxygen end of the molecule partially negative. And the hydrogens are partially positive. So here they're showing water molecules just maybe in a little bit different model, where we've got kind of this like bigger bubbly looking atom, and then there's some little atoms on there. Well, the bigger atoms should be the oxygen, and the little atoms are the hydrogen, and they're kind of trying to show them in their bent structure. Get out of there. Okay, so that's kind of how they're showing these water molecules in the picture. The oxygens are in red, and the little hydrogens are kind of like whitish blue. Water is polar, very polar, meaning that it's got these charged regions. Well, those charged regions are going to be attracted to anything else that's charged. What's something that's always got a charge? An ionic compound. Ionic compounds are composed of charged ions, fully charged ions. So those ions are very attracted to the water molecules in a way so that opposites attract. So check out this picture in here. We've got our salt, we throw it in the water, and here we know that the salt would be like a crystal. So they've got these green and orange charged ions that are in this crystal structure where they're packed real tight and very organized. Well, then you get these water molecules, and the water molecules work on the crystal one ion at a time, and they surround an ion in a very organized way so that opposite charges attract. So these little orange ions are supposed to be the sodium. The sodium would be the positive ion, right? The sodium plus 1 ions. Well, check this out. Do you see this in here? Here's a positive sodium ion, and the water molecules surround that ion so that opposites attract. And so it's the negative oxygen end of the water molecule that starts to surround the orange positive sodium ion, and eventually then the water molecules totally cover the sodium ion and they remove it from the crystal. And then this is called a shell of hydration, where you've got that ion, that positive orange ion, sodium ion, and it's totally covered with water molecules. Look what happens to the negative chlorine ion over here. Whoa, no joke. Opposites attract. The water molecules have both charges, positive and negatively charged ends. So now when I have a negative ion like chlorine, the water molecules will orient themselves and surround the chlorine ion so that the positive hydrogen end of the water molecule is attracted to the negative ion. And eventually they totally cover that negative ion and rip it right off the crystal. And so we say then that solutions are really stable. Like once I dissolve salt in water, it tends to stay that way. Well, yeah, it's because these ions are never really in direct contact with each other. They can move around in the solution, but they always are covered with these shells of hydration. They're always covered by these water molecules. Now, obviously, you can evaporate the water, and then the sodium and chlorine ions will go back into the original crystal, and they would exist as a solid again. But as long as they're in solution with their little shells of water molecules, they're very stable. So in question 37, we want to draw a model showing the solvation of potassium chloride in water. Well, it's going to be really similar. That eventually, let's say I've got a potassium ion. Well, potassium forms a +1 ion. I could put a +1 in there. And then there will eventually be some, what do we got? Chlorine ions. -1. There's my chlorine ion. Well, they're going to start out looking just like this. This could be sodium chloride, potassium chloride. It starts off looking like a very organized crystal structure, where it would just now be oppositely charged ions of potassium and chlorine alternating throughout the solid. And I dissolve them in water, and the water molecules work their magic. So if I have a positive ion, the water molecules are going to organize themselves so that it's the negative oxygen end that surrounds the potassium ion. So I'm going to draw some little water molecules. And it's no accident I want the bigger oxygen end to be closer to the potassium, because it's the oxygen end that's partially negative and the hydrogen end is partially positive. Oh, cool. Then when I dissolve the chlorine ions, it's going to be the opposite. Now I'm going to draw my water molecules so that it's the positive hydrogen end that's attracted to the negative chlorine. These little baby positive hydrogens that are attracted to the negative chlorine. They'll always align so that opposites attract. So here was the partially negative oxygen, but I want the partially positive hydrogen to form a shell of hydration or a shell of water molecules that will totally surround that ion. And again, these guys will be pretty stable. They'll swim around in the solution until I do something like evaporate the water. So when we talk about like dissolves like, and we know that water is polar, very polar. Anytime I use water as my solvent, only other things that are polar will dissolve in water. Now, ionics are as polar as it gets. Polar just means that your substance has oppositely charged regions. Well, yeah, I mean, ionic has oppositely charged ions. It's crazy polar. It's got really strongly charged ions. But you could also dissolve any other molecule that's polar, that would have these oppositely charged regions that would then be attracted to the oppositely charged regions of a water molecule.